starting off with solutions first. For solutions, we have some concentration terms, that is mole fraction. Firstly, we have mole fraction. Mole fraction is like, if you want to calculate the mole fraction of first component, the number of moles of first component divided by the total number of moles of all the components present in that mixture. Okay, and the mole fraction of all the components is equals to unity. Next, we have molarity, that is number of moles of solute divided by volume of solution, that is in liters. Here units are very important. This is in liters. And molality, we have mass of solvent, that is in kilograms. Next, we have Henry's law, where P is equals to KH, and mole fraction, where P is the partial pressure and KH is the Henry's constant. Next, we have the colligative properties. Very important. The questions are usually asked from colligative properties and Van Hoff factor. So we have 4 colligative properties. First, starting with relative lowering in vapor pressure. Always remember, in my all the formulas, I'll denote second to 2 is equals to solute and 1 is equivalent to solvent. If I'm denoting something 2, that means I'm talking about solute, and with 1 I'm talking about solvent. So here we are going to see this is the relative lowering in vapor pressure, but P naught minus P is the lowering in vapor pressure, where P is the partial pressure and P naught is the pure vapor pressure. Okay, pure vapor pressure, and P is the partial vapor pressure. So this is relative lowering and this is the lowering in vapor pressure, that is equals to mole fraction of solute. Okay, this represents solute. Next, we have elevation and boiling point. The boiling point is increased after adding some solute here. So delta TB is equals to TB minus TB naught is equals to KBM, where KB is the molar elevation constant. Okay, so here the units for KB are also mentioned here, that can also be asked, where M is the molality. Always remember, with relative lowering in vapor pressure, we have that is equals to mole fraction, and here we have molality. In depression and freezing point also, the formula is very similar. It's just that here we have TF naught minus TF, because here we have depression, the temperature is getting down, the freezing point is lowering. Okay, there is depression in the freezing point, and this is equals to, this is also molality. But in case of osmotic pressure, always remember this, in case of osmotic pressure, that is dependent on the molarity, not the molality. First we have mole fraction, then molality. Here also molality, here we have molarity. This is pi. Pi denotes osmotic pressure is equals to CRT, where C is equals to molarity. Okay, so molarity is what? Number of moles of solute divided by volume of solution in liters. Next is, if we want to calculate this, if there is any dissociation or association, so there will be Van Hoff factor. So just apply the Van Hoff factor in all the formulas. Just I will be here, I will be here, here also I will be here, and then I is added, here also I is added in all the colligative properties. In all the colligative properties, because of association and dissociation, there will be some change. Next, we have Raoult's law. For Raoult's law, this is the partial vapor pressure, this is the vapor pressure in pure state, okay, denoted by naught. This is the mole fraction, right? If something obeys Raoult's law, that is called ideal solution. If do not obey Raoult's law, this is called non-ideal solution. Okay, we have positive, negative deviations, and you need to remember all the examples of positive and negative deviation as well. Next, we have Van Hoff factor. For Van Hoff factor, the I is equals to observed colligative property divided by calculated colligative property, that is also equals to number of particles after association or dissociation divided by number of particles before that, okay, initially. Then we have normal molecular mass divided by observed molecular mass. Here you will calculate the I and put in the colligative properties. So also, how to, if there is dissociation, then colligative property is related to degree of dissociation with this formula, and the Van Hoff factor is always greater than 1 for dissociation, and Van Hoff factor is always less than 1 for association. Here it is related to degree of dissociation with this formula, right? Okay, so now next we have electrochemistry. Very important and very scoring chapter, So let us understand the formulas. There's just few formulas, but very important formulas, especially Nernst equation. So let us see, this is anode, this is cathode. This is a representation of cell. Here at anode there will be oxidation, at cathode there will be reduction. That means here we have loss of electron, here we will have gain of electron represented by this. This is the salt bridge here. Next we have how to calculate E cell. How to calculate E cell? That is equals to E cathode minus E anode. That will be that means cathode is on the it is on the right side, so that will be E right side, that minus E of left side. You can also calculate this E right minus left. You can also see it like this, cathode minus anode. But always take the reduction potential, never oxidation potential is taken here. Always take the reduction potential in both the cases, right? Next we have how they are related to each other. So standard reduction potential is directly proportional to oxidizing power, and it is inversely proportional to reducing power. Next we have Nernst equation. For Nernst equation, this is the formula where it is E cell is related to E naught cell with this formula, where log here on the above we have oxidation and down we have reduction. Okay, the thing that is getting oxidized and thing that is getting reduced. Okay, next we have standard condition temperature is standard, right? For that, and log is based to 10. This is the natural log. This is log based to 10. For that, this will be the formula, that is 0.0591. Just always remember these two formulas, because if you're not given the particular temperature, standard temperature, then you will apply this formula. If you're given the standard temperature or you're not given anything, that means you have standard temperature only, then you will apply this formula. Okay, where R is the gas constant. Next we have at equilibrium E is equals to 0 and delta G is equals to 0. So the formula becomes, just put these value here and the formulas becomes like this. Okay, now this whole chart is very important. The question are asked from this. Next we have Gibbs free energy, that is related to delta G is equals to minus NF E cell, where F is the 1 Faraday, that is 96500, and this is the relation between delta G and delta G naught. Naught means the standard conditions. Okay, here spontaneous reaction is where E cell is always greater than that is positive, greater than 0, and delta G is negative, that is less than 0. For non-spontaneous, E cell is less than 0 and delta G is positive, that is greater than 0. Next we have this formula again, beta, let us see this. So these are related to conductance and resistance, resistivity, very important. So see this is the R represents here, just firstly see what this represents. R represents resistance, rho represents resistivity, C represents conductance, and kappa, this is called kappa. Kappa represents conductivity. So these are the units of these particular terms, right? Next we have cell constant, that is represented by G star, and that is L by A. Units can be per centimeter or per meter, and the R is related to resistivity in this case. This is conductance is related to this conductivity in this case. Okay, so these formulas are very important. Next we have molar conductivity. Now this kappa represents the simple conductivity, but if we want to calculate the molar conductivity or equivalent conductivity, for that the formula is molar conductivity is equals to kappa into 1000 divided by molarity. If kappa is in centimeter, is in Simon centimeter inverse, this would be Simon centimeter inverse. If it is in Simon meter inverse, the 1000 will not be here. Okay, similarly with molar equivalent conductivity, that is kappa into 1000 divided by normality. Usually molar conductivity is asked. Okay, so now next we have the infinite dilution. At infinite dilution, that is limiting molar conductivity, that is related, if we want to calculate, they will ask you, firstly they will ask you to calculate this thing, then they will ask you to calculate the degree of dissociation. Degree of dissociation is molar conductivity at a concentration C divided by molar conductivity at infinite dilution, that is limiting molar conductivity, and from there you will calculate the Kc, that is degree of dissociation constant. Okay, so dissociation constant is equals to C alpha square 1 minus alpha. Okay guys, so this is also asked. They will ask you firstly this, then this, they will take you this. Okay, this delta, this for calculating the molar conductivity at infinite dilution, there are 2-3 things that we can do. Okay, for that we have Cauchy's law. For this Cauchy's law, we have this. This simply says that if you have an anionic compound, in that compound, this N, this particular things, they represent that molar conductivity at infinite dilution will be equals to the molar conductivity of individual ions. Okay, these are the molar conductivity of individual ions, limiting molar conductivity of cation, limiting molar conductivity of anion. What is this N? What is this N? This represents the number of cations and the number of anions that they are being dissociated into. Very important. Firstly, they will let you calculate this molar conductivity in infinite dilution from this law, then molar conductivity at C concentration from this one, and after that you have to calculate the degree of dissociation, then dissociation constant. Okay, next we have Faraday's law. We have two laws, that is first law, second law. This can also be asked. Usually students avoid this, but this can also be asked. Very simple. So firstly, this is W. W is the weight, the mass or the weight deposited, right? Z is the electrochemical equivalent, I is current and T is time, and Z is equals to E by F, and E is equals to molar mass by N. So the formula becomes MITNF, where M is the molar mass, F is the Faraday, that is N96500, N is the number of electrons that are gained or lost, and I is the current, T is the time in seconds. Okay, so now second law says that if we have so many things that are connected in series, for that weight of metal at A divided by weight of metal at B will be equals to equivalent weight at A, equivalent weight at B. Okay, so now next we have chemical kinetics, very most simple chapter of physical chemistry, very easy chapter of physical chemistry. Then we have reactants and products. Here you have 2-3 things that students usually get confusing. Let me teach you that. So firstly, this is the average rate, that is equals to minus. Minus means that is getting disappeared. Okay, so the reactant is getting disappeared, minus is for that, and the product is getting formed, the plus is for because it is getting formed here, it is not getting disappeared. Okay, this is the rate of appearance, this is disappearance. So this is delta. Delta represents a large change and D represents a very, very small. So this is R instantaneous. R means rate at instantaneous. Okay. So this is dr by dt. This is delta R by delta T. This is delta P by delta T. This is dP by dt, because this is a small change, this is a large change. Okay. Next we have rate of, this is not a very large change as comparative to D, this is a large change. Okay. Rate of reaction. What is the rate of reaction? What is this, ma'am? Let me teach you this also. So if you have this particular reaction, there are two things. Okay, they will ask you 2-3 things. Firstly, they will ask you rate of appearance. Rate of appearance means that is getting appeared. So this is getting appeared here. This should be positive. Wait. This should be positive here. This should be positive here. Okay, because it is getting appeared, no? So appearance means it is positive, disappearance means that should be negative. So here it will be negative here, right? So rate of appearance, for calculating the rate of appearance or disappearance, you need not divide that with any moles. Okay, here I have not divided that with 1 by A or 1 by B. Okay, but if you are calculating rate of reaction is always calculated for 1 mole. So because of that, you will also say rate of reaction will be equals to, this is for appearance and this is for disappearance. This is for disappearance. So rate of appearance, rate of disappearance, and also write the number of moles. That's why I have written rate of reaction is equals to appearance or disappearance 1 by moles D, whatever will be the reactant or product, divided by dt. So always divide it with the moles. Why? Because we calculate for rate of reaction for 1 mole only. So this is very important. Usually students get confused in this. Next we have the simple formulas, that we have this reaction. So the rate law, according to rate law, rate is equals to K A raised to power X B raised to power Y. So X and Y in equilibrium constant, we have written A and B. That was because of raised to the power stoichiometric coefficient. Here we do not have raised to the power stoichiometric coefficient, rather these are actually experimentally done. So X plus Y or all these forms together form the order of that reaction. So X plus Y is the order of that reaction. It has nothing to do with this reaction. You cannot find the order of reaction by just seeing that reaction. It depends on the slowest step, right? Okay, so now rate is equals to rate constant, and for rate constant and the X plus Y is the order of reaction, that I have written X and Y is not equals to A or B, nothing to do with A or B, right? Next we have X plus Y is equals to 0, that is 0 order reaction, it is 1, then first order it is 2, then second order 3 is equals to third order. Okay, you have only these 3 orders of reaction in your syllabus. Okay, so now how to calculate they can directly ask you what is the unit of rate constant. Okay, they will give you the order of that reaction. For that we have this simple formula where N is the order of reaction, mole per liter, 1 by N second per second. Okay, so this is rate constant units. They can ask you, these questions are directly asked in the exams. Okay, next we have the formulas of 0 order, first order and second order reaction. For first order reaction, this is K represents the rate constant, this R naught represents the initial concentration, and R represents the concentration at that time. Okay, so T is the time, right? So T half is the half time, that means where half of the concentration is consumed and half is left. Okay, so for that R naught by 2k, they can also directly ask you the half-life period of zero order reaction directly depends on the initial concentration. For first order reaction, it does not depend on the initial concentration. These type of question can also be asked directly from this chapter. Okay, so first order reaction, k is equals to 2.303 log R naught by R, then T half is equals to 0.693 divided by k. It does not depend on the concentration, right? Only depends on the rate constant. Next we have second order reaction. So this is the relation between rate constant and time and the concentration. For half-life, we have 1 divided by initial concentration into k. So this is inversely proportional to the initial concentration, right? Okay, so next we have the Arrhenius constant, and what is activation energy? This is A is Arrhenius constant and this EA is the activation energy. The formula, this is the rate constant, this is the direct formula, right? After this, applying this formula for one particular temperature and other temperature T1 and T2, we had this, that is log K2 by K1 is equals to EA 2.303 R, T1 minus T2, T1 into T2. So you will be given two temperatures and you have to calculate the activation energy or something like that. Some terms will be missing here, and this formula is also very important for your numericals.